Hello everyone. This is our first topic for exam 2. Inverse trigonometric functions and integration by parts is what exam 2 is devoted to. And we start in topic 1 with just a review of the theory of inverse functions. Regarding functions in general, you might recall I've mentioned before the acronym Y8, which gives us the 5 main classes of functions. L is for logarithms, I is for inverse trig, A is for algebraic, T is for trigonometric, and E is for exponential. And so in Calculus 1, you mastered algebraics and trigonometrics, differentiation and integration of those. We just got finished with logarithmic and exponential. So now our focus is on the inverse trig functions. Now this acronym will become a hierarchy for us a little bit later. But first, just to review inverse functions in general. Here's the formal definition of the inverse trig functions. Basically, the composition has to equal x, and we studied this before when we talked about logarithmic and exponential functions because they were inverses. And remember the composition when we write, for example, f, the little bubble symbol g, so f composed with g of x, it really means that x first goes into g and then that result goes into f. So that little bubble symbol is just notationally meaning f of g of x. So we have an inner function and an outer function. The inner function, in this case g of x, the outer function f of that. So we talked about this concept as well, mapping. If you have, let's say, an oval that represents a set, and we'll call this the domain of the function f. And there's a bunch of elements in this set. You can picture them as little dots. Let's just focus on a general element, call it x. And, for example, if the function f of x were equal to the square root of x, this is just an example, the domain of that function would be that it must be greater than or equal to 0. No negative numbers under a radical. So that would be the elements that are in here. But we're talking about this in general. So if you take an element x and you send it through the function f, then you produce its image, f of x. And then if you take all the elements that are in the domain of f and send them through the function f. So if we take all the elements that are in the domain of f and send them through the function f, that produces a new set. And we'll just call that the range of f. And then we want to define the inverse function. And the inverse function is basically the function that undoes whatever f did to that element x. So basically, if g is the inverse, we could take the result, f of x, and send it through g. And if g is in fact the inverse function, it should bring us back to x. And that is then g of f of x, which is the composition of g with f. So you can see that that's why the definition must be true. The composition has to equal x, bring us back to where we started. And similarly, if you started with an element, let's say over here, we'll call that the domain of g, and we send it first through the function g, we get the element g of x. But then if f is the inverse, that would undo whatever G did, and as long as the range of F, or the range of G is in the domain of F, then sending that element G of X through F should bring us back to the element X, and that's F of G of X. So that's the reason that's a nice, way to picture the abstract thought of the composition. But basically, the inverses will undo whatever the function does, right? Now, graphically, and we saw this before as well, inverse functions are reflections in the line y equaling x. So if you had, let's say, for example, a function where, I'm just going to sketch this arbitrarily, and choose a deliberate function though. It's really the square root of x minus 1, but I'm not going to even name it, I'll just sketch it. And let me call that f. The inverse, in a moment we're going to realize how we could tell that this function has an inverse just by inspection. But for now, just trust me that it does have an inverse. And if it does have an inverse, then the inverse function graphically is a reflection in the line y equaling x. So if we draw the line y equaling x, which bisects the first and third quadrants, then we have to use our spatial senses and imagine reflecting over this line. Okay, so symmetry, essentially. And if you remember algebraically, finding the inverse function, what we did was at one point we interchanged the x and the y's. And that's what it means when you reflect in the line y equaling x. You let x be y and you let y be x. So this point, which is the point 1, 0 in the reflection, becomes the point 0, 1. And that's true for all the points on this graph. So then we would get in the reflection something that looks like this. Now we've been calling it G, but let's get used to this notation. I'm going to say F with a superscript of -1. So F with a superscript of -1, you read as F inverse, or the inverse of F. Okay, so get used to that superscript of -1, and it has nothing to do with negative exponents. It's just a notation that we use to indicate the inverse function. Okay, and then we start with some other definitions. First off, a relation is any set of ordered pairs. And then you should recall this from like pre-calculus. And a function is a relation, so it's a set of any ordered pairs, but it has this restriction, such that for every value of x in the domain, there is exactly one value of y in the range, meaning there cannot be two y values for the same x value. And so we have, as you should recall, a vertical line test for functions. And we say a relation is a function if a vertical line passes through its graph in at most one point. That's one way to say it, at least. Because if a vertical line passes through the function in 2 points, that means for that specific x value, there would be 2 y values, and that's not allowed because there has to be exactly one y value. So here's some examples, just quick examples. Let's say determine if the relation is a function. So I'll just throw some graphs up here. So here's x, y. Let's just consider a circle centered at the origin. Okay, if you took a vertical line, straight edge, ruler, whatever, pass it through the graph, and you could see, if it's not hitting it at these points, that's okay. That just means it's not in the domain. You know, it hits it at one point on the edge, but then you get inside the graph, and it hits it in more than one point, right? So a vertical line, let's say, would hit it at, in this case, at 2 points, which means for that particular x value, there's 2 y values. And that would mean that it's not a function. Okay, how about a parabola? Let's say a parabola concave upward. We'll take the vertex at the origin. Again, don't worry about the equations. All right, now pass a vertical line through the graph, and again, straight edge, ruler, whatever. Everywhere you see this vertical line just passes through the graph in 1 point at the most. So yes, it is a function. Let's consider a parabola that instead of being concave upward or downward, let's say is open to the left or open to the right. So something like that. Okay, this one is you take a vertical line, pass it through the graph. Again, over here, it's okay. That's just not part of the domain. Hit it at 1 point at the vertex, but then when we get inside there, looks like the vertical line hits it in more than 1 point. So therefore, it's not a function. And let's just consider one more. How about that same parabola, but instead of the entire thing, let's just take the top half of it. And so, yes, we have a function, because a vertical line hits it in at most 1 point. Okay, continuing with the theory, here's a definition that you may or may not have seen. If you did see it, you probably didn't spend a lot of time with it. But it's for a characteristic that we call one-to-one. First off, you have to have a function. So we say a function is one-to-one if for all all pairs of x values that are not equal, x1 not equal to x2, we have that their functional values are not equal. F of x1 is not equal to f of x2. Now, when you first read that, it doesn't seem like it makes a lot of sense, but if you take the time to sketch out the idea, the graphical meaning, or analytical meaning, it will make a lot of sense, because, for example, what it's saying is, can I draw a Cartesian system? It's saying you have 2 different x values. So let me just call this x1 and this x2. So that satisfies this first condition. It's saying for all pairs of 2 different x values, the functional values cannot be equal. So for example, if x1 had produced this image, call it f of x1, then x2 could produce pretty much any image that it wants except that same functional value, because f of x2 has to be different than f of x1. So let's say it can be anywhere, I'm going to use an open, anywhere except there. That is, it could be above, it could be below, way above, way below, it doesn't matter. But what it's suggesting then, similar to the vertical line test, is what we're going to call the horizontal line test. So a one-to-one function would be such that you cannot have 2 points along the same horizontal line. And that is the horizontal line test. We say a function is, first off, it has to be a function. Okay, it's 1 to 1 if a horizontal line passes through its graph in at most one point. Okay, and so let's look at an example. It says to determine if the relation is a function, and if it is, determine if it's 1 to 1. Okay, we're not going to talk about the circle, but let's talk about the parabola that is concave upward. And it really doesn't matter where the vertex is, but I'll put it at the origin. Okay, so first off, is it a function? That's the vertical line test, and you can see vertical line passes through it in at most one point, so it is a function. But is it 1 to 1? Well, if you take a horizontal line and pass it through the graph, you can see there's a situation, there's an instance, many instances, of course, where a horizontal line intercepts this function in more than one point. So therefore, it's not 1 to 1. Okay, what about that parabola that was open to the right? Okay, well, first off, it fails the vertical line test. That is, a vertical line hits it in more than one point. And so, therefore, this is not a function. So, by definition, if it's not a function, it has no chance to be 1 to 1, because if you look back up here, by definition, it says a function is 1 to 1. So it has to be a function first in order to even have a chance of being 1 to 1. So since that's not a function, we don't even need to talk about the notion of it being 1 to 1. So then what's a function that is 1 to 1? Well, that would be that sketch I showed a little earlier where we take half of this parabola in number 2. So top half, bottom half wouldn't matter. So there's an example that is a function because it passes the vertical line test, and it is 1 to 1 because it passes the horizontal line test. So here's the Monumental Theorem. This is the type of theorem that you would prove in a junior level math course. Okay, so it's beyond what we're going to prove here, but it says if a function is 1 to 1, then it has an inverse. So now we have a way to tell that a function, by inspection of the graph, we have a way to tell if the function has an inverse, and that would be if it's 1 to 1. So the classic example, just to show it once again, if we had that half of a parabola, top half, something that opens to the right, let's say, and we'll call that F again. Draw the vertical line, y equaling x, because graphically, remember, inverse functions are reflections in the vertical line, y equaling x. And also this point 1, 0 becomes the point 0, 1 when reflected. Use your spatial senses, and the graph is going to look something like that. And again, we're going to use this f with the superscript of -1 to indicate the inverse. So here's something kind of interesting. I called it a fact. And as they are defined, none of the 6 basic trig functions actually have an inverse. And so at this point, you're probably saying, great, he's just wasted 20 minutes of my life, because he started out by saying we're going to study the inverse trigonometric functions, and now he's telling me that there aren't any. But there's a way around it. But the reason why we say as they're defined, the trig functions don't have inverses is because consider the graphs. Like, for example, consider the sine of x. Just a rough graph. Sine oscillates between 1 and -1. Goes on and on forever in either direction. So this is y equals sine of x. And the reason why it does not have an inverse is because it's not one-to-one. It is a function, because a vertical line passes through its graph in at most one point, but the horizontal line passes through its graph in an infinite number of points. I mean, draw a horizontal line anywhere where y is between -1 and 1, and you've got an infinite number of points, okay, where that horizontal line intercepts the graph. So the reason why it does not have an inverse, so let's say there's no inverse, I'll say cos, just to abbreviate, because is cos, it's not one-to-one, because it does not pass the horizontal line test. And this holds for all 6 trigonometric functions. Cosine, same thing, except it's shifted by 90 degrees instead of having a starting at 0. Cosine function starts at 1, so the axis is basically shifted by 90 degrees. But for the same reason, there's no inverse, because it's not one-to-one. The reciprocal functions, cosecant and cotangent, or excuse me, cosecant and secant, that's just taking the sine function. You don't really have to know these graphs, but they're actually kind of easy to understand. At the high points and the low points, at the zeros, there's actually asymptotes, vertical asymptotes, because you're taking the inverse, or not the inverse, the reciprocal, or 1 over. So then the y-axis actually becomes a vertical asymptote as well. And this is what the graph of cosecant looks like. And you can see it's still not one-to-one, right? Because again, these are cyclic, they go on and on forever. And the tangent graph too. If you think of what the tangent looks like, there are vertical asymptotes at pi over 2 and negative pi over 2. And then tangent looks like this. But it repeats itself every pi radians. So let's say if that's 3 pi over 2, halfway between, let me get rid of this arrow. Halfway between pi over 2 and 3 pi over 2 is pi. And that would be where it crosses. And then it's got that shape for the tangent function. And that repeats itself every pi radians, and so you could see that a horizontal line passes through its graph in more than one point, so therefore that's why it's not one-to-one, and therefore it does not have an inverse. But the way we get around that is by doing the following. We're going to restrict the domain of the trigonometric function so that it is one-to-one, and therefore will have an inverse. So I'm going to stop right there for this video, and we'll come back and we'll do a part 2. So we'll see you when you are ready.